Hi, everybody. Recently, the world record holder for having the highest IQ, YoungHoon Kim, came out on social media and said that he was Christian. Now, he based this on some very interesting reasons, and he explained that his reasons were related to quantum mechanics. So, how do you get from quantum mechanics to a belief in Christianity? Well, in this video, we're going to explain exactly that, while providing a very accessible explanation for quantum mechanics that I think a lot of new listeners might really appreciate. But first, before we get to that, just as a quick plug for the channel, we are a very new channel. So if you like this video, if you click the like button, that really does mean a lot for us. If you subscribe to the channel, that also really helps us out tremendously, especially since we're such a new channel. And I also want to encourage you to click the bell icon so you don't miss out on any notifications about future videos. Now, maybe the most important thing to me personally is that you add your comments to the comment section. I've really enjoyed a lot of the comments that you all have had about a lot of my videos, and they really have changed my mind about a lot of different things. So if you comment in the comment section, that's a really wonderful way to me that I find very enriching to keep the conversation going. Now, first of all, why did I want to talk about this topic for today's video? There are a couple of different reasons. Maybe the most important one is I actually wrote a paper about this that got presented at an international society meeting in Argentina, and that paper is now in the scholarly literature. In that paper, I sort of established my connection between simulation theory and theology, which I think is very interesting, and maybe I'll link to that paper in the comments section. So that's the first reason why I was very interested in talking about this topic. The second reason why I wanted to talk about this is because YoungHoon Kim, in his statement, says something really interesting about how he reconciles science versus religion, which is what he says is that you can look at the universe and ask two sets of questions. One is why-type questions, and the other is how-type questions. So one set of questions is more questions about why. The other set of questions is questions about how. Now, what do we mean by this? So let's look at some of our how-type questions. How did the universe get to be here? How did the universe get to look like it is? How did galaxies form? How did stars and planets form? Those are all questions that you can answer through the sciences. And maybe we don't have all of the answers to all of those questions, but we're starting to get pretty close on some of those questions. So I think those are all sort of how questions. They're all sort of mechanistic, and they all describe sort of links in the chain of causality. Now, on the other hand, if you look at the universe in a way that's theological, you can ask a different set of questions, and those are sort of why-type questions. So those are questions that ask why. Like, why are we here? Why is there something rather than nothing? Why did God create us in the first place? These are all questions that are of a very fundamentally different nature than the more causal or more mechanistic how-type questions. So if you've followed this debate at all on social media between atheists and apologists, you may have come away with the perspective that there's sort of a scientific way of looking at the universe, and then there's a sort of more religious way of looking at the universe. Well, I think my point here is to explain that you can do both of those things simultaneously. Now, there are sort of fringes of where how and why type questions inform each other and sort of bleed into each other. But on the other hand, you can sort of think of this as a different set of questions that you can ask religiously or spiritually that will maybe change the way you see yourself in relation to the universe and might influence your perspective on the sciences a little bit, but it doesn't really have to influence your perspective that much. So in other words, the debate that we get exposed to frequently on social media is a bit of a false dichotomy. I really like what YoungHoon Kim said because he emphasizes this point. And by the way, I've written an entire book about reconciling science with spirituality that goes into a lot of depth around how-type questions and why-type questions, and maybe I'll put a link to that book in the description. All right, now let's get into the meat of what YoungHoon Kim's arguments are about theology and quantum mechanics. So first of all, unfortunately, we need to give you a bit of a brief summary on quantum mechanics. Now, that term is very scary, so people don't really understand what quantum mechanics means. So I'm going to explain it in a way that I think is pretty accessible and pretty simple and still gives you some new insights that you can maybe bring into your spiritual life, or at least engage with some of the sciences in ways that are more interesting because you have a little bit of understanding of quantum mechanics and hopefully aren't so intimidated by it. So very simply, quantum mechanics is the science of things that are very small. So we're talking about things like electrons and photons. They seem to behave in ways that defy classical logic or the way that we experience the universe macroscopically or at a human scale. So, for instance, things can be in multiple places at once, things can influence each other at a distance, and weird behaviors can emerge if you look at the world through a lens that's quantum mechanical. So we have to basically come up with a different set of rules when we're looking at the very small structures of quantum mechanics. Now, I think that this can actually be explained very simply with a very nice analogy that explains exactly what quantum mechanics is. And our analogy that we're going to use is just a light bulb. What we're going to do with this light bulb is we're going to pass electrons through a filament. That's going to heat up the filament because we're creating a current, and that creates luminosity or light. Now, what I'm going to connect to this light switch is a dimmer switch, right? So I can set this dimmer switch at any angle I want or any elevation that I want, and that's going to control how many electrons flow through the filament to generate a current to then generate light. Now, let's say that we make our dimmer switch exquisitely sensitive to very small flows of electrons. And then what we're going to do is we're going to measure how much light is given off by the light bulb with, again, a very, very exquisitely sensitive measuring device that can detect very, very tiny amounts of light. So we can start to create a slope that the higher we make the dimmer switch, the higher we position it, the more luminous the light bulb is and the more light there is in the room. And when we make that slope, it's very clearly a straight line. So the more current I let through the filament, the hotter the filament gets, the brighter it gets, the more light is emitted, and the more light we collect in our detector. So this is very clearly going to be a very straight line of slope. Now what we're going to do is we're going to put the dimmer switch at the lowest possible setting. So this is going to be just one tiny little electron each time that's going to cycle through the filament to create just a very minuscule amount of light. Now, if we only let one electron through that filament, and again, we're making some assumptions of physics and mechanics in doing this experiment, but if we let only one electron through that filament at a time, what we're going to see is the light will actually flicker on and off. Now what we're going to do is we're going to slowly increase the current by increasing the elevation of the dimmer switch. And as we do that, we're going to see the light gets brighter as we let 2 electrons through, 3 electrons, 4. Now, what we'll quickly start to realize is that instead of a straight line slope, what we have is some stair stepping that gets created. So if there's 2 electrons going through, that's sort of one level, 3 electrons is the next level, 4 electrons is the next level, and as we let more electrons through, we'll see that the bulb will get brighter and brighter. Now here's the very critical point. We can't let half an electron through. You can theoretically split an electron into its component parts, but from a quantum mechanical perspective, there's something that's unique and quantizable about the electron. So that means that essentially it's indivisible from a certain perspective. So let's just work with the assumption that it's indivisible. So that means that there are certain steps in between these steps that we've drawn in our slope where you can't sort of access those intermediate positions. And the reason is because we've said we're letting 1 electron, 2 electrons, 3 electrons through, but we're not letting 3.5 or 4.5 electrons through. So you can exist on any of these steps, but you can't exist on any point in between the steps. Now, this is just like walking up a set of stairs if you think about it, right? You can't be in between stair 1 and stair 2, right? You can be on both steps at the same time, but your feet can't be on step 1/2, right? So this is exactly the way the quantum mechanics works, is when we look at very, very small particles, they seem to have this very unique property, especially photons and electrons have been really well validated to have this set of properties where they exist on stair steps. So let's look at an atom now, right? An atom is a nucleus which is positively charged with a proton and maybe a neutron or maybe a few protons and a few neutrons, and it's surrounded by electrons. Now, if we add energy to this atom, we can get those electrons to go into a higher orbit, but we can't get those electrons to go in between orbits. In other words, we can only add energy to the atom itself through adding discrete photons. So again, it sort of acts like a stair-stepping pattern. And we'll see this motif of stair-stepping or quantization over and over and over again in quantum mechanics. And that's the reason why quantum mechanics has that word quantum in front of it, because things are very quantized in quantum mechanics. Now, I won't get into all the details about quantum mechanics, but I will say this. When we look at such small scales, things happen in very weird ways. Particles can be in multiple states or places at the same time until they're observed. Particles seem to pass through barriers that they shouldn't be able to pass through, and they can also seem to pop in and out of existence out of just empty space. And also just watching a quantum mechanical system can seem to change the outcome of an interaction that we're measuring. So this set of rules is very interesting. There are some explanations, but ultimately we don't really understand why things work the way they do on the quantum mechanical level. There are a lot of different explanations, But this is kind of a common thing in academic disciplines. If you ask someone for an explanation of why something happens and they say, well, there's like 5 or 6 or 10 or 15 different explanations for why this might be happening, that means that there are some things that we don't understand. When we start to understand something really well, we sort of boil it down to one explanation of actually what's happening. But anyway, so quantum mechanics is this process of quantization. Things look very stair-stepped when we look at certain scales. And we start realizing that quantum mechanics has, a weird set of behaviors when we look at such a small scale. It's almost as though when we look at such small scales, the universe becomes very pixelated. So imagine like looking at a computer screen and then you stick your face right up against this computer screen, or you turn the resolution way down. Well, you'll start seeing individual pixels. Now we're going to jump to a different topic, but it's related to quantum mechanics, and that's the topic of information conservation. Now, this is a really fascinating idea. You're probably already somewhat familiar with this idea from the conservation of matter and energy. Maybe you learned in, grade school physics that, matter can never be created or destroyed, but it can be turned into energy. And the same is true of energy. Energy can't be created, it can't be destroyed, but it can be theoretically converted into matter. Well, in the 1960s, Rolf Landauer hypothesized that because you can only store information in physical ways by, using matter, either a human brain or a computer chip, that because of that, information ought to be susceptible to the same laws of physics as matter itself. So what Landauer was essentially saying is that there must be a law of conservation of information, that information itself can never be destroyed. So what that means is that you can scramble information, certainly, and you can sort of hide information, but you can't get rid of it. So this principle means that in theory, if you had complete knowledge of a system's present state, you could reconstruct its entire past and also predict its future. Now, this is very interesting because this sounds a lot like omniscience. Now, we're going to get to this a little bit more, but most physicists now believe, especially from looking at black holes, that there is a law of conservation of information. Now, there's a specific way that the black holes preserve the information of their contents, but we'll get into that in just a moment. But first, we need to explain what a black hole is and what the event horizon of a black hole is. So, let's imagine that we're in a rocket ship and we're trying to escape from the Earth's gravitational field. Well, we need to reach a certain velocity to kind of overpower gravity. So we need to accelerate beyond a certain point to be able to sort of penetrate the gravitational field of the Earth. Now, let's imagine that we could somehow magically increase the Earth's mass. So we're going to make the Earth more and more and more dense. As we make the Earth more dense, that gravitational field is going to increase, and that means we need to go faster and faster to be able to escape the gravitational field of the Earth. Now, you could imagine theoretically that you make the Earth's gravitational field so massive that even if you traveled away from the Earth at the speed of light, you wouldn't be able to escape the Earth's gravitational field. Now, this is actually exactly the thought experiment that led people to first conceptualize that there might be such a thing as a black hole. And that's all a black hole is. A black hole is a body that is so gravitationally dense that even if you traveled away from that body at the speed of light, that you could not get away from it. Okay, so there's two parts of the black hole. There's sort of the singularity at the center of the black hole, which is just a gravitationally dense object, right? And then there's the gravitational field around the black hole. So that gravitational field is the area around the black hole, or the volume of the space around the black hole, where even if you were traveling at the speed of light, you couldn't get away from the black hole. Now, this leads to some interesting ideas. Like, let's say, for instance, that you're inside that field of volume, that volume of space, where even if you traveled at the speed of light, you couldn't get away from the black hole. Well, that means that the black hole is in front of you in every direction that you look. So if I'm looking at a black hole as I'm traveling towards the singularity, if I've crossed the event horizon, then even if I turn around 180 degrees, the black hole is still in front of me. That singularity at the center of the black hole is still in front of me in both time and space. Now, we're not going to get into a lot of those thought experiments, but they are kind of interesting to think about. So the black hole is usually thought of as the singularity, which is the gravitationally dense body, and the event horizon around the black hole, which is the volume of space where nothing can escape, even if it travels at the speed of light. Now, that means that no event, no information that happens inside the event horizon can travel to the outside of the event horizon. So you can kind of think of that event horizon as the gravitational well itself. Now, the reason why it's called an event horizon is because it contains information, but that information becomes, in a way, inescapable to the outside universe. Now, Stephen Hawking said that, well, wait a second, if I toss something in the event horizon of a black hole, then that information becomes lost to the universe forever. But in 2017, after a decades-long debate, Gerard de Tooft and Leonard Susskind proved that there is still a way that you can actually get that information to the outside universe. And that way is, and we're skipping over a couple of important details, so I'm just oversimplifying things, but it's not that much of an oversimplification. But the way information can travel to the outside world is based on the actual contour of the event horizon. So it's as though an apple that you throw into a black hole will sort of linger on the surface of the black hole, and that information will sort of, stay static. So it's as though the event horizon converts the apple that you've thrown into the black hole into a matrix of ones and zeros. It becomes very much a binary-looking information matrix on the surface of the black hole. Now, this is really interesting because this means that all of the information about all of the volume inside the black hole is all expressible by a two-dimensional surface on the surface of the black hole. So you can kind of think of the black hole event horizon as a volume of space, but that surface is the event horizon. That's actually a two-dimensional surface, just like any surface of a sphere is two-dimensional. Now, what we've learned over time is that if you study a black hole, the same rules that govern a black hole and its physical reality also have to govern our universe itself. In other words, you can't have a different set of rules for the universe and a different set of rules for black holes. So that means that the universe itself must also have an event horizon. Now, this is very interesting because it means that there's three-dimensional reality inside of the universe, and that three-dimensional reality generates information. But there is an imprint of all of that information on the surface of the universe. So the universe itself has an event horizon. That means that there's a two-dimensional surface somewhere out in space beyond our reality. And that means that all of the information that we experience is just as real in the frame of reference of that two-dimensional reality. Now, that gives rise to the holographic principle. So what is the holographic principle? It sounds like an intimidating phrase, but what it means very simply is that the universe is like a hologram. So there's two-dimensional information of the universe, and that gives rise to the three-dimensional reality. Just like when you hold a hologram, it's actually two-dimensional information that creates the illusion that you're looking at something three-dimensional. So that's the principle of the universe as a hologram, and we'll come back to this in a second. But first, we're going to switch gears, and we're going to talk about why does this information, because now we've talked about a few things. We've talked about the law of conservation of information, we've talked about quantum mechanics, and we've talked about how the universe has an event horizon. Why does this mean that there's a God? Well, there are a few different reasons. So I'll list 4 different reasons. There are actually several others. But here's one that's fairly easy to explain. So first of all, oftentimes when we find information anywhere in nature, we almost always find a conscious entity that is capable of processing that information. So any matrix of information is often followed by a sort of understanding that that information will somehow be processed. So we can kind of say the same thing for the event horizon of the universe. There is that information out there. It's readable. So that sort of implies that there's a reader of that information. All right, reason number 2. If omniscience from a perspective beyond the universe is possible, then there is reason to believe that it must exist. Murray Gell-Mann in the 1960s won the Nobel Prize for his work on quantum mechanics and basically figuring out how subatomic particles interact to form the Standard Model. Now, you don't need to know why he won the Nobel Prize, but the point is what his research showed is that the universe seems to be totalitarianistic. Now, usually when we say totalitarian, we mean that, it's guided by an authoritarian regime or a governmental entity. But what Murray Gell-Mann means when he uses this word is slightly different. It means that anything that's possible in the universe is compulsory. So if we say that something could exist, then that means that it by definition has to exist. That seems to be a motif that we often see when we research the physical world or the universe or even quantum mechanics in general, that what we see as possibilities are things that we can ultimately prove to actually exist. So that's what Murray Gell-Mann says. And if we look at the event horizon of the universe in a way that's totalitarianistic, then we can say that the existence of that event horizon suggests that at the very least it's possible for an entity beyond our scope of understanding outside of the universe to be conscious of everything that's happening in the universe. So if omniscience is possible, then the totalitarian principle suggests that omniscience therefore must exist. All right, here's the third reason. If we sort of start thinking of God as a multidimensional being who can interact with our reality on a lower dimensional level, then we can start explaining what would look like a mechanism for the powers of God. Now, I know this sounds very convoluted and a little bit contrived, but there's an easy way to explain it, which is just by analogy. So let's come up with a thought experiment. Let's say I find a magic wand And this magic wand is capable of doing anything. It's very powerful. So what I do is I use it to create an entire universe. But I'm just going to create a two-dimensional universe. Okay. So in other words, this universe is, doesn't have any third dimensionality to it. It's completely flat. And then I populate that universe with beings. It would be very easy for me to convince those beings, if I could interact with them, that I do have magical abilities. For instance, I could take one finger and put it into one aspect of their reality in one location, and I could put another finger elsewhere and put it into another aspect of their location. Now, these beings exist two-dimensionally only, so they don't have any conception of how I could be in two places at once. So to them, that seems like a really magical ability. Now, we can't really reconcile all of the omnipotent capabilities of God with this thought experiment, but it's easy to start, if you start thinking about it more carefully, it's easy to see how you could sort of interfere with this two-dimensional world in ways that seem very magical and very remarkable to its inhabitants, while on a higher dimensional level, you're not really violating any laws. So in other words, omnipotence at least is explained partially by understanding our universe as a lower dimensional projection of information in two dimensions. So I hope that makes sense. I know it's a little bit complicated, but here's a fourth reason why understanding the universe as from a quantum mechanical and holographic perspective gives us an understanding of why God might exist. So that fourth reason is the following. And we've sort of danced around this a few times in this video, and I've made another video that goes into this more extensively. But if reality is indeed a simulation, then it's likely that there is some entity that created that simulation. So here's another way of explaining that. Where else do we sort of see examples of pixelation in realities, or where else do we sort of see places where there's a holographic simulated reality? Well, at least one example is just computer games. So computer games are sort of ways that we simulate different realities. Now, we wouldn't call those authentic realities because we know how we created them, we know who created them, and we know that they're computer games. But if we start seeing the same principles happening in our universe, things like pixelation, things like the holographic principle, then that sort of leads us to the conclusion that, well, maybe the reality that we are experiencing isn't quite an authentic reality, but maybe it is also a simulation. Now, if the universe, our universe, is a simulation, then this suggests that there's a simulator. If it's a computer program, this suggests that there's a programmer. Now, another way you can think of this is the following. Nick Bostrom is a big proponent of simulation theory, and he makes the case that if any species, any time in history, can create a simulated reality that's convincing, then it is far more likely that our universe is just one of many simulations. Now, here's the problem with his analysis, is that it is just, you can apply his same reasoning to the universe of the simulator, right? So, in other words, if we are in a simulated reality, and there's an alien species that created our simulated universe, then it's just as likely, based on Nick Bostrom's analysis, that that alien species is also living in a simulated reality. So that means that there's an additional reality that's sort of outside of their experience. Well, now you see what the problem is, because now you have an infinite regression. So you basically have shells and shells of simulated realities creating other simulated realities, and there's no prime authentic reality. One very easy, very neat, very persuasive and parsimonious way of explaining how this can all happen without leading to this problem of infinite regression is just say that there is a God who created our universe as a simulation. And that really wraps everything else up in a much more neat way, and you don't have this problem of infinite regression. So there are four reasons why some of the things that we've talked about in this video, quantum mechanics, conservation of information, and the holographic principle, all lead to the idea that there might be a God within the universe. Now, let's turn our attention to Christianity specifically and talk about why Christianity might be a very neat-looking reconciliation of a lot of the ideas that we've had. All right, so here's some ideas why all the principles that we've talked about might lead us back to Christianity. So first of all, we have sort of a reconciliation of the Trinity, right? So we have sort of a Trinitarian modality for God, or a Trinitarian paradigm. Here's why. Because we've talked about God as a consciousness outside of our universe. But as in our magic wand example, God would have created the universe. So there would be sort of an imprint or a presence of God within the entire universe. So you can kind of think of that as the God outside the universe as like sort of God the Father, and the God inside the universe as God the Holy Spirit. So the God that imbues the universe to make it exist, and the God that's outside of the universe to be conscious and to be sort of externally judging. It also makes sense that if someone did indeed simulate a universe, it would make sense that that individual would likely at some point incarnate into the universe to experience the existence that they had created. And this is what we see with Jesus. So all three components of the Trinity are very nicely explained by the Trinitarian perspective on God. Now, here's another reason why Christianity seems to more likely be true in light of this idea of a simulated universe with the laws of quantum mechanics that are observed. And that is that Jesus often poignantly says that this world is not the ultimate goal that we should have for our experience. In other words, and I've made a whole video about this, so I won't recap all of those points, but Jesus often, if you kind of think about the teachings of Jesus, says you shouldn't focus too much on your worldly wins and losses in this life. In other words, Jesus is saying, don't worry about the material existence too much. Don't worry about collecting too much. Don't worry too much about, what material goods you're going to have in the immediate or longer term future. Instead, worry about things that are more transcendental. Now, this kind of makes sense, and it takes on a much more beautiful poignancy when you kind of think of the universe as just a simulation of some reality that exists external to our experience. In other words, if Jesus is indeed saying, hey, there's more to this reality than what you're experiencing, then that has a lot more poignancy if we view the universe as a hologram, and if we view the universe through the lens of quantum mechanics, as we have throughout this video. So this makes Jesus' statement sort of inherently more appealing. Now, here's the third reason, which is, I think, really nicely articulated by YoungHoon Kim, and that is that Christianity is a window through providing understanding when we hit the limits of science. Now, we've talked about some really complicated things in this video. So we've talked about quantum mechanics, the law of conservation of information, the holographic principle, and we've sort of tied them together with simulation theory to describe why that means that there's likely a God. Now, if you're watching this video, I bet some of you already believe in Jesus and you're already Christians, and this video maybe has provided some interesting and more nuanced education about the universe that we live in, but maybe it's not really moved the needle that much for you in how you believe. So I think that's very interesting. One of the things that YoungHoon Kim says often is that the beauty of Christianity is that it provides a lens for understanding our reality, even if we aren't really complete in our scientific understanding. So we've talked about kind of a very esoteric way of looking at Christian theology. But on the other hand, a lot of you already believe in Jesus. So even if you have a much more simplistic view of the universe, there is still this way that Christianity can be a bit of a gap filler. So if you understand a lot about the universe, or if you understand very little about the universe, Christianity can still fill in those gaps in nice, interesting, and fulfilling ways. I think that's a really interesting idea. I didn't really fully appreciate that until I looked at the writings of YoungHoon Kim, even though he's just made I think, a couple of social media posts. Now, that brings us sort of close to the close of the video. I just want to highlight that I don't mean to speak for any other individuals. I just thought YoungHoon Kim's ideas were so similar to my own that they were worthy of discussion. But he does believe for other reasons, so I want to acknowledge that you should check out his videos, you should check out his social media presence. Some of the other reasons why he believes are that, the beauty of the messages of Jesus is, he just feels like Jesus has very beautiful messages, and that some of the goodness of Christianity really transcends pure reason. So there are ways that you can be good in Christianity that aren't so intellectually and maybe as over-intellectualized as this video would have you believe. So anyways, that sort of brings us to the close of this video. I do want to say again that if you've made it to the end of the video, I'm super, super grateful. I'm really grateful for your support. I'm really grateful to the people who have weighed in on the comment section. And I know that we've talked about some really esoteric concepts in this video, but I really am grateful that you've stuck it out. I hope if you have gotten to this point that you've come away with an understanding of science that is more fulfilling. And I would love to know if that's true in the comment section. In other words, comment in the comment section and let me know what you think of these ideas. Let me know if some of these are new to you, if some of them really resonated with you. I'd really super love to know that. All right, and moreover, we're a new channel, so I would really love it if you like this video. So if you click the like button, that really does help us out. I put a lot of work into these videos, so liking each video really helps us massively more than some of the bigger channels out there. I would love it if you subscribe to the channel. That really does help us out a lot. Please click the bell icon for notifications so that you don't miss out on future videos. And once again, I would just really love it if you all comment on this video so that we can keep the discussion going. All right, well, thanks very much. I'm a professor, and these are some ideas that I'm very passionate about, so I really appreciate being able to share them with you. So once again, if you've made it to the end of this video, thanks so much for paying attention for so long, and as always, please have a really wonderful day.